Welcome to our next lecture on transformation matrices within the course of computer graphics at KAUST. On the last lecture, we have been recapitulating some linear algebra basics and looking at linear algebra from a geometric perspective. Here, on this lecture, we will turn linear algebra into a useful tool in transforming objects within 3D or 2D spaces. So we can express any linear transformation two-dimensional, in this case, by a matrix which is representing the various factors associated with x and y coordinates. So at the beginning, as an input, we would have some x and y coordinates of certain points corresponding to maybe triangles or centers of spheres or other primitives. And these can then be transformed into some other x and y coordinates. So this would be the new x coordinate, and this would be the new y coordinate after such a linear transformation. A simple linear transformation, just to bring us a little bit up to speed, could be scale. If we have a look at the scale matrix, we can see that this is a diagonal matrix which is having an element Sx and as the first element in the first row and the Sy as the second element in the second row, both on the diagonal. And what such a matrix does for us, the outcome of the newly transformed coordinates x and y. So these two will be simply scaled version of these. And as we see, there is an x scaling factor and y scaling factor. So these two coordinates will be scaled independently from each other. Then we will be talking about a non-linear scale, non-uniform scaling, and in case when the Sx equals Sy, we will be talking about uniform scaling. And such is the case in the image which we have here on the right side of the slide, where Sx and Sy are having value 0.5, and both of these will scale our coordinates by the half distance from the origin. So it is important to understand that x and y are now certain coordinates here. This is the origin of our coordinate space, and the coordinate x will be now the new coordinate will be half of the input one for both x and y. So we will end up in a representation which looks like on the right hand side for both the let's call these points, let's call this point P1, and this will be more correct to call it P1 new, and this point will be the P2 new, this will be P2, this will be, let's say, P0, and after scaling P0, which will be at position, so that's P0 has coordinates 0, 0, the result will be 0, 0 after the transformation. Multiplying 0 will result in 0. And then we have the point P3, which has the coordinates x and y, and the P3 new will have the coordinates x half, y half. Pretty simple. So we are, as you can see, transforming certain points in space, And then using this transformation, if we will be transforming all 4 points of this rectangle with the texture of the clock, then we will be transforming the entire rectangle uniformly. We will be scaling it. If we will, however, change our scaling factors from uniform to non-uniform, I will just remove this so that you can see the picture clearly, then we see here that the X scaling factor has remained, but the Y scaling factor has changed to 1.5. And as we can see, our intuition is supported, where we can see that the Y scaling got much bigger than the X. And this corresponds to all these points which have been transformed. And then if we have a texture on this rectangle map, then this texture will be also changed. Another linear transformation is shearing. Shearing means that we are just changing a representation. If we will have again this example of the rectangle, we will be simply creating a parallelogram out of this rectangle, and the shearing has the term, the shearing term is located here. So it will effectively create us that in the x coordinate, we will now, because we have an off-diagonal element, will be some contribution of the y, which is scaled by the value s. As there is 0 in the second row, there will be no contribution of x for the y, so the y input will equal to the transformed y. But the higher the value the y is, the more there will be a translation of the x position along the x direction, and the higher the y, the more this translation will happen. So if y is 0, there is the x coordinate is unchanged, and with increasing y, this x coordinate will be more and more sheared. Interestingly, this factor s also corresponds to the angle of shearing. So if we look at this angle between the x-axis and um, uh, the side of this rectangle, which is now mapped to a side of a parallelogram, the side of the parallelogram makes with the x-axis an angle which is the phi, and in the matrix, shearing matrix, this we will have a factor tangents phi, which will be corresponding to this shearing amount. So the scaling factor of shearing in the off-diagonal position, we can see that we can predict how much this shearing will be. If we have in the first row, the off-diagonal element equals 0, then similarly to the previous case, the x coordinate will not be changed, the transformed x. However, if there is a transformation in off-diagonal non-zero element in the second row on the first position, then we will have again shearing, but not along the horizontal direction, but along the vertical direction. And here, the similar will hold. The higher will be the x value, the more the shear factor will be for that particular x value. So, but the same holds, we will again have the factor S will be tangents phi for this factor. So we can predict how much will be this factor changing the geometry in terms of shearing. Another very important linear transformation is rotation. So how can we express rotation in through matrices? We have already been talking about that rotation is corresponds to an orthogonal matrix, which consists of two, in two-dimensional case, orthonormal vectors, and these vectors will be then corresponding to a rotation. This is partially true. This statement I need to revise because such a definition also holds for reflections. And reflections and rotations are two different transformations. However, for rotation transformation, the determinant of our orthogonal matrix is positive and equal to 1, while the determinant for a reflection matrix will be negative, equal to -1. So let's have a look how we can derive the matrix for the rotations. If we look at the transformation between Cartesian coordinates and polar coordinates, we will agree that if we have a certain point A represented by the polar coordinates, we can derive its Cartesian coordinates through, so this will be the XA and this will be the YA through R times cosine alpha, so a projection of the R onto the X axis, and for the Y coordinate, it will be projection of the R onto the Y axis through the sine function. We know that this R is its size corresponds also to the square root of each of these coordinates squared. Now, what is the value of for xb? xb, we actually do not have here angle for the point B in polar coordinates, but what we have are two angles, and their sum will actually correspond to some angle under which we will find the point B in polar coordinates. So let's just that we are having it a little bit clear, let's define an angle theta which is equal to alpha plus phi. And this angle theta will be here. So it will hold that for xb we will have r times cosine theta. But now let's express it as the sum of the alpha and phi, because this will have this will show us how we can derive the properties or the coefficients for rotational matrix. So if we look at r times cosine theta alpha plus, which is alpha plus phi, we can, this sum in the cosine term, we can also rewrite into a slightly different form, which is this r times cosine alpha cosine phi minus r sine alpha sine phi. So this is from the high school mathematics and an equivalent form, and we can write it this way. Interesting aspect shows up here, and that is that we suddenly have here a term r times cosine alpha, and here we have the term r times sine alpha. What are these terms? Well, we can have a look here. Actually, we find out that this term is actually xa, and this term is actually ya. So they are the coordinates, Cartesian coordinates of our point A. So if we would like to now change the A into B, this is the way how we can get out of coordinates of point A to coordinates of point B, and that is through a multiplication with either cosine phi, so the angle spanned between the vector A and the vector B, and for the y and minus the y coordinate of the point A and multiplied by the sine phi. So this is great. We already see how these are the input coordinates, and this would be the output coordinate. So far we have been talking only about the x coordinate, but we see that for the y coordinate, something very similar is here. It's slightly different because this is the r times sine theta, which corresponds to alpha plus phi. But here we can see that there is a similar formula. And also we see here that there is an element which corresponds to ya, and here is an element which corresponds to xa. This is fine. So we can use this to somehow create a matrix so that these elements will be then multiplied correctly with the corresponding uh, factors. So let's have a look how we can perhaps do it. So here we have our matrix. We don't know the elements yet. And here we will have, let's just keep the xa and ya, and it should be equal to xb, yb. So what do we need to multiply in order to get the xb? What do we need to multiply xa and ya with? Well, we can see for xb, we need to multiply the x with cosine phi. So here will be cosine phi. And here we multiply it with minus sine phi. Can you see that? And for the y, what should be the coordinates? For the associated with the xa will be the sine phi. And associated with the ya will be the cosine phi. And we can also appreciate that this matrix looks pretty orthogonal to us because these two vectors are orthogonal to each other. And also we can see what will be the determinant of such a matrix. Let's have a look at the determinant. This will be, of this matrix, will be, so cosine phi minus sine phi, cosine phi is equal to cosine squared phi, cosine squared phi minus sine squared phi, and this is equal to 1. So it is also these are orthonormal vectors, and this is a rotational matrix, as we have discussed before. Here we see the matrix once again, and here we can see already the devised matrix, which we were just devising on with a pen. We can see the result here right away. Let's try to apply such a matrix and perform certain rotation. So if we have a certain point, we can use our rotation and get some new point. So let's have a look at this without doing this with math, or we can in principle. So we can have this one particular rotational matrix, which is 0.7 minus 0.7, 0.7, and 0.7. This matrix is actually where the sine phi is equal to cosine phi, and that is when phi equals to pi 4, 45 degrees. So now, with this matrix, we will be rotating our points in the space when multiplied with this matrix by 45 degrees. We will be rotating them around the coordinate origin, which is here. So let's put a point 0, 1 there, just because that one is also shown here on the graphics. We can also see that point 0, 0 will not be rotated, it will stay where it is, and that makes sense. And other points on the corners of this rectangle will all be rotated. So let's have a look how much is the point 0, 1 rotated, and we should be rotated by 45 degrees. We can see that this on the graphics this holds because it was at the vertical axis, and now it is 45 degrees away, counterclockwise away from the vertical axis. So let's just try to have a look what will be the new coordinates if we multiply this. So 0 times 0.7 is 0, and 0 minus 0.7 times 1 is 0.7 minus. Okay, and for the y coordinate, well, it will be again 0 times 0.7 is 0, and 1 times 0.7 is 1. So this is 0.7. And we can see that the x-coordinate is now minus 0.7, and the y-coordinate has also shrunk from 1 to approximately 0.7. So this holds what we have now just exemplarily tried out. Let's have a look at a very similar but yet different transformation, which is the reflection. You can see here a one reflection, which is a reflection along or around the vertical y-axis. So all x points will change their sign from plus to minus. We can see it here. This makes sense. If I have x and y here, then what will happen at the output, I will have minus x and y. So the y values will not change, but the x values will change. And that simply can be observed here in this image, where all the positive values have flipped onto the other side, and we have achieved the reflection. Let's have a look whether this matrix is also orthogonal matrix. And yes, we can see that these two vectors are orthogonal to each other, minus 1, 0 and 0, 1. But what is the determinant of minus 1, 0, 0, 1? Well, this is super easy to calculate because nothing is off diagonal, which is equal to -1. So this is a reflection matrix. Now, we can also reflect around the x-coordinate axis. And here we have done it. We have simply just put the negative value and negative multiplicator um, to the second row on the diagonal, and we have now flipped the coordinates to the around or along the x-axis. Seems to work fine. Now this was only with ones on the diagonal, plus or minus. However, we can combine reflection and scaling together by having non-unit vectors present in such a matrix. So if on the diagonal we will have a varying sign, however, there will be not ones in the diagonal but other numbers, this will correspond to a reflection and a scaling. There could be several reflections if we have for example, if we will have a reflection of x and y after each other, what will be that? Let's try to multiply -1, 0, 0, 1, and 1, 0, 0, -1. What is the result of such a matrix? So -1 times 1 is -1, and 0 times 0 is 0. So we have -1 here. And then for the second term, -1 times 0 and 0 minus 1 is 0. And then for the second row, 0 times 1 and 1 times 0 is 0. And for the last one, 1 times 0, 0 times 0, and 1 times -1 results into -1, -1. These two are forming us also two reflections. However, these two reflections, actually two consecutive reflections, form us a rotation. So two consecutive rotations form a rotation, two consecutive reflections cause a rotation. So here we can see what is here. This is the cosine phi is equal to -1, and sine phi is equal to 0, right? So yes, this is a rotational matrix, and we can also see that if we will be calculating the determinant of such a matrix, -1, -1, 0, 0 is 1. So it is a rotational matrix. It's also orthogonal matrix, and therefore what will be the angle? What is a cosine phi equals to -1? Well, that is cosine p. So the phi in such a case will be equal to p. So we can see that there is a tight correspondence between reflections and rotations, but they are not the same. Now, we have so far performed just one operation, either it was shearing or rotation or scaling or reflection, but you will believe me that we can, after we have transformed the point, we can transform it again and again and again. So what does that mean? Imagine that we have transformed one point, V1, by a matrix which corresponds to scaling. So S corresponds to scaling here. And this will be the point V2. So our transformed point V1 will be point V2. Now, if we rotate the point V2, we will end up in the point V3. So if we want to express the point V3 with respect to point V1, this will be the corresponding formula. So first, the V1 needs to be scaled in order to become V2, and then V2 is rotated so that we get the V3. This calculation of matrices is not commutative, but it is associative. So we can first actually compute the product of two matrices and then multiply the point V1 with the product of these two matrices, and we will get the point V3 straight away. So now M matrix is the product of the matrix R and S, and this product is then bringing us from the point V1 straight to the point V3. We can see this here on the following figure, where we have our first transformation will be scaling. So this is the matrix S here, and brings us from one point. Let's take this one as being the point V1. And this point V1 will then be scaled, and it will result into a version of V1, which will be the V2 point. And once we have this point V2, we can rotate it. We are here rotating by some values. From these values, we can already see that the sine and cosine values are the same. So we are dealing with the 45 degrees rotation. And yes, we can see here how this has rotated 45 degrees. And our point V2 is transformed into point V3. Great. Now, if we have the point V1 and we have our matrix M, then we will end up in the point V3 directly from the point V1. Please keep in mind that the first transformation, if we have a concatenation of transformations like T1, T2, T3, and so on, T4, and our vector V, which we want to, or point V, which we want to transform, then first we are multiplying with the T4, then the resulting coordinates we will be multiplying, post-multiplying with T3, and then with T2, and then T1. Not in the left to right order, as somebody might be tempted to do. However, in the case of product of these two matrices, R times S, this is the correct order. So it's not that we will be now changing the matrix M to be S times R. It is the order needs to be kept as it was when we performed this associative rule change. Let's have a look whether our matrix M has indeed these coordinates. So if we are now multiplying the matrix S, 1, 0.5 times 0.7 minus 0.7, 0.7, 0.7, if we now multiply these two matrices, then our resulting matrix will be, here are zeros, of course. So 1 times 0.7 is 0.7, because this second term is 0. And then 1 times minus 0.7 is minus 0.7. And here we have a similar situation. 0.7 is times half is 0.35. And 0.7 times 5 is again 0.35. And if we have a look here, we will find out that, these two matrices are not equal to each other. Why? Which mistake did we make? Well, let's have a look. So here we have these values, the half values in the lower row. Did we make some numerical error? Or did we make an error that we wrongly ordered the matrices? So this is the S matrix and this is the R matrix. Oh yeah, so we should have multiplied the R with S and not S with R. That's why they are not the same. So be careful, this is not a commutative operation with concatenating matrices. If you concatenate them wrongly, then you will end up in a different transformation. Oh, and we can see it right here. What is the result? This is what we have calculated, and this is what was calculated before. This is the matrix M, and now let's have a look. So what are we doing here? We are first here in our original case, M is RS. So first we are scaling and then rotating. So this is M. And first rotating and then scaling. So that was SR. This is us. As our matrix, which was wrongly calculated on the previous slide. So we can see that we are here first rotating because the R is on the right side and then scaling. And these two results aren't the same. So our point V, which was this point, will here end up at this position, while here it will end up at this position. So these two transformations are not the same. Let us calculate an rotation, scaling, and rotation, which will result into an scaling along an arbitrary axis if one rotation will be the opposite of the other one. So what it will be if we are performing a rotation along the, so let's say we have one point. This point, just for simplicity, will lie on the x-axis, and now we are rotating it by 45 degrees, so it will end up somewhere here. Now we have first, no, but this is wrong because we have started again from the left side. We need to read it from the right side. So this is wrong, forget about this. And now we have this 45-degree rotation. And now we have the scaling, where we scale the x-axis with the 1.5 and the y-axis with 1. So we will have here an scaling which will correspond to the 1.5. We will be somewhere, maybe here. So we will be here and 1. So, sorry, the y will be 1. So we will be here. And then we will be rotating back. So this vector, we will then be rotating back by 45 degrees. It is more visible what is happening if we will have some point already at the 45 degrees to begin with. What will happen with it is that first we will rotate it to the y-axis, then we will be scaling it by 1.5 in the x direction. But x is 0, so it will be not scaled at all, and 1 will be will remain the same, and then we will rotate it back. So to this point, nothing will happen. And what will happen to a point which will be originally at position which is minus 45 degrees from the x-axis? It will be rotated into the x-axis, then it will be scaled by 1.5 factor, and then it will be rotated back into, again, 45 degrees. So this is a scaling along an arbitrary axis, and this axis is, in this case, an axis which spans with the x-axis minus P4 angle. And we can concatenate such a matrix with this formula. You maybe recognize it because this looks like some decomposition of a symmetric matrix which we had in the linear algebra lecture. Let's have a look at this once again. How do those matrices look like? So this matrix will look like, this is 45 degrees, this matrix with minus P4, so this is a minus P4 will still be, so cosine minus P4 is equal to 0.7. Let's have a look at it at our unit circle. So minus P4 is this value here, and it will map to 0.7 something, and approximately, but for sine it is minus 0.7, so the sine minus P4 is equal to minus 0.7, approximately. So in our matrix, we will have the terms 0.7 minus sine minus minus, so it will be 0.7 here, and then we will have here minus, no, here will be plus sign, so we will have minus 0.7, which is this value, and cosine will be again 0.7. So this will be our first matrix, this matrix here. And then we will have our scaling matrix. Oh, that is simple. So it's just 1.5 and on the diagonal and 1 on the diagonal in the second row. Now let's have a look at the other matrix, which is the P4 matrix. And actually, it is the transpose matrix, as it says. So let's just try to transpose this matrix. 0.7 minus 0.7, 0.7, 0.7. Well, we just perform the transpose of the R, and we can see that the R is a rotation by minus pi 4, and the R transpose is the rotation by pi 4. So we can see that here. And we can see that if we will now multiply this matrix, we will end up in a matrix which should be symmetric. If we would calculate this concatenating these three matrices together, we will end up in a matrix which will be 1.25 approximately minus 0.25 minus 0.25 and 1.25, which is a matrix which is certainly symmetric, and you can do the multiplication as an exercise yourself to see whether we really indeed end up in this matrix. So we have already now seen that the correspondence between eigenvalue and eigenvector decomposition of symmetric matrices, what does it have as a geometric meaning? Let's have a look at the previous matrix from some time ago, from the last lecture on linear algebra, where we had this matrix A, which was equal to 2, 1, 1, 1. And this matrix, what is it? Now we can see here that this matrix is again a decomposition of a rotation followed by and scaling and followed by an inverse rotation. So this is its corresponding meaning. So we can see that first we are rotating this the points in this space by this matrix, and this matrix has a cosine is so cosine of this matrix will be positive, the sign will be negative, so it's we are rotating in the minus direction, and the cosine will be 0.85. So let's draw a small unit circle here, and we can see this will be 0.85, and this will be minus 0.53, so somewhere in the middle. And these two are then meeting somehow. I didn't draw it very nicely, but it looks like it's around the 45 degrees, but it is a little bit more than 45 degrees. Sorry, it will be less than 45 degrees, and it will be something more like 30 degrees, minus 30 degrees. So we can see here that first we are rotating the object by minus 30 degrees, and then so this point will get much closer to the x axis, and this will go somewhere here approximately, and then we are performing the second operation, will be performing a scaling, non-uniform scaling, where the y-axis is scaled, is miniaturized, right? While the x-axis is almost 3 times factor. And then we will be scaling back by the 30 degrees, and then we are resulting into a putting the points back where they were after the scaling operation. So we have now been scaling the points in the space along the 30-something axis. So along this 30-something axis, we have been scaling the matrix in a very strong scaling along that axis, and in a smaller than 1 scaling in the axis which is perpendicular to the axis as along the approximately 30 degrees. The concatenation of matrices, if we know the matrix, if we know the matrices and keep track of them, we have a big advantage that we can undo certain operations, meaning that even if we forget where the points previously were, if we perform simply a chain of inverse operations, then we can reach the original points where we started. So, for example, if I am performing let's say, a scaling, rotation, and maybe another scaling, So this is S1, S2. Then if I want to perform an inverse operation of this, then I will first, so the inverse operation of this will be S2 will be first inverse applied, because this was the last operation which was performed before. Then the rotation, which will be inverse, and then the scaling, which we started off with, will be also inverted. So with this operation, we will end up where we started. And we can also prove it if we now perform this concatenation of operations and these ones. We can see that these two matrices will form as an identity matrix, and then there will be, which could be then removed, and then these two matrices will form as an identity matrix, which could be removed, and then these two matrices will form as an identity matrix. So there will be no transformation happening. Let's just have a look at the other case of non-symmetric case of a matrix, where our matrix can be decomposed into with the singular value decomposition. So we will end up into an orthogonal matrix U, and then a scaling matrix, and another orthogonal matrix V. So what can we achieve, for example, with this type of matrices? It depends on the particular matrix, but for example, we can achieve by this decomposition, we can achieve by that an operation which we already know. Let's have a look from the previous case in linear algebra. You remember we had this matrix A, so where this matrix, if it was product of this matrix with its transpose, was then the matrix 2, 1, 0, no, 2, 1, 1, 1. And here we have the matrix 1, 1, 0, 1, which, well, 1, if we just eyeball this matrix, we can see that there is a 1 and 1, which is an identity. And here we have, what is this? This is a shearing factor by 45 degrees, right? So this matrix is a shearing matrix. And we can have a look. This shearing matrix, you can see here that this is a shearing along the x-axis, so a horizontal shear. That's great. And what does this shear correspond to if we decompose it? So it corresponds to a rotation, and then it corresponds to some scaling, and then it corresponds to, again, some rotation, which is not the inverse rotation of the first one. So we can see here, what is this? So if we again eyeball this a little bit, we can see that this matrix on the unit circle, 0.53 will be for the cosine, and the sine is minus 0.85. So we are somewhere here. So now we are more than 45 degrees. Let's have a look. Okay, this is minus 58.3 degrees. This is the first rotation by minus 58.4 degrees. Then we have the scaling. Along x-axis, we can see that we are performing much stronger scaling than along the y-axis on this rotated object. And then we are performing a rotation, which is this we already had. this was around 30 degrees from the previous case, and here you can see, yes, it's 31.7. So then we are rotating it back, but not completely back, but just partially back, and we end up in shear. So shear transformation can be decomposed into rotation, scaling, and rotation matrices. As the last topic of the two-dimensional transformation case, we will discuss the decomposition of rotations. So far we have decomposed some scaling along arbitrary axes into scaling and rotations, and then we have decomposed the shearing into rotations and scaling, and now we are decomposing rotations into what? So here we have it already written for us, and we can see that the decomposition into these three matrices, and let's start with this one. So let's say A, B, and C matrix. They all are what? Well, the A and C is equal to A, so this is A again, and this one is different. So what does it do? Well, we can see that there is one, this is a diagonal matrix, but there is off diagonal one value which is non-zero. So this is a shear in horizontal direction, and the A and C are both shear in horizontal direction. And then we have, what do we have there? We have a shear in the vertical direction. So we can see that first we horizontally shear some object, then we vertically shear it, and then we again horizontally shear it. So this is the first transformation. This is A. Here we have then the B, and here we have the C, which equals to A again, and we have achieved a rotation by, what is it? By 45 degrees. Plus 45 degrees. And we can see that the terms which are necessary for that can be calculated here. So 45 degrees is here 0.7 something minus 1 divided by 0.7. This will be minus 0.3 divided by 0.7. So this is approximately something less than 0.5 minus 0.4, let's say, something like this, can be the result. So we can see that this is approximately corresponding to this shear because it's negative and the shear goes this direction. So it seems like this is correct. And then we have this sine phi. So this is a shear by 45 degrees. So this will be here, we will have the 0.7 value. Please keep in mind that for the shear, this will be tangents of this value, not the sine, of course. So, but we are now expressing the rotation and angles by the shear factors. And the term here is again minus 0.4. So these three shear factors will constitute a concatenated together will form as a rotation. What this can be good for? This can be good for a raster graphics, actually, because in making a rotation with sort of pixelated input with already discrete samples, this can lead to various types of problems. But if we are, as you can see here, just shifting rows by a certain offset, and then shifting columns by a certain offset through the shear transformations, then we will end up in much better realized rotation. So for raster images, it is beneficial to change a transformation of rotation into a transformation of 3 consecutive shear operations. After we have sufficiently discussed the 2D transformations, let's have a look at 3D linear transformations, which can be also expressed through matrices, but obviously these matrices will no longer be 2 by 2 matrices, but they will be 3 by 3 matrices. So for scaling, for example, we can use a matrix, which will be a diagonal matrix, and on the diagonal there will be the individual scaling factors for each coordinate direction, as we had previously, but with the added value for the z coordinate, as we would expect. So if these 3 values will be the same, we will deal with a uniform scaling, and if one of them or 2 of them will be, or 3 of them will be different, then we will deal with non-uniform scaling. Here we have an example, another 3 by 3 matrix, and this is an example of a shear. We can see that the shear matrix has now 2 components because both the distance along the y-axis and the also distance along the z-axis will play a role in how much are we shearing the x-coordinates. So, of course, one of them can be equal to 0, but in general, this is the representation of a shear axis. Now, let's have a look at the rotation matrix. So, while we were not so much aware of it, in 2-dimensional case, we were sort of rotating around an axis which would be the z-axis, which was pointing to our 2D plane. So rotation around the z-axis takes us in the same way as we were used before. So the x-coordinate and the y-coordinate are determined in exactly the same way. There will be zeros for the contribution from the z-coordinate. So the last column will be having 0, 0 in the first 2 rows. And then there will be in the third coordinate, we will have 0, 0, and 1, which means that there will be change of coordinates of x and y, and the coordinate z will remain the same, which makes sense if you think about that. If we are rotating around the z-axis, the z value should not change, should be the same after the rotation. Before we go to rotation around the y-axis, we will have a look at the rotation around the x-axis, and we can see that this rotation also looks as we would expect. So there is the x-coordinate is unchanged and therefore is having this 1 here and 0 elsewhere. So the y and z values are not affecting the x value, and the x value remains the same after the transformation, and the y and z values will be changing according to the to what is expected by the cosine or sine values in the second and third column of this axis, because they are corresponding to the y and z axis. Very similar, but slightly different, we will see is the behavior of the y matrix if we rotate around the y-axis. Here we see that again the y for the y-axis there will be no change because 0 is stands for the x-coordinate, and for the z coordinate, and for y coordinate there is 1. So the y values will remain constant. How about the x coordinates and the z coordinates? This will of course change, and the cosines and sines are at some logical positions. However, the sine is somehow of the sinus function, not in the expected position of the x row, a negative sign, but it's actually in the third row as the first place. So this is somehow changed. And what is corresponding to this change? It has something to do with the right-handed coordinate system and left-handed coordinate system. So if you look at the right-handed coordinate system, in the right-handed coordinate system, you will always somehow have a right-handed coordinate system. If you look at, for example, from the so this will be the x, y, and z axis. If you look at the coordinate system from the positive z direction towards the origin, the projection here will be x, y. If you do something similar along the x-axis, you will have a similar projection, which again, which will be, so this will go to the top, this is the z, and this is the y. So these are both right-handed coordinate systems. But if we will look from the y direction, actually we will see that there is a let me turn this, and we can see that along the y-axis, this is the z-axis, and this is the x-axis. So suddenly, this has a not the right-handed coordinates, but left-handed coordinates. Therefore, we have to switch the sign in order to have the rotation of along the y-axis behaving in the same way as the other rotations. So in the other cases, we want, for example, if we are rotating around the x-axis, we will rotate the y-axis into the z-axis, and if we will put our thumb of the right hand aligned with the x direction, we will see which direction is the y-axis rotated towards the z-axis, and something similar will be expected for if we have our thumb aligned with the z-axis, and the x-axis will then rotate into the y-axis, but along the y-axis, the x-axis is rotating into the minus z-axis. So therefore, we want this effect to happen. Therefore, our sine value has to be positive in the row and in the first row, and negative in the third row. You can look up this information for more details. We can also rotate around arbitrary axis, and we will prepare a framework how to do it. Imagine we have an arbitrary rotation consisting of 3 vectors. Now let's consider 3 row vectors. So this is the vector u, this is the vector v, and this is the vector w. And if we will be multiplying the vector u with such a matrix, post-multiplying, we will end up in the value 1, 0, 0, which means that if we have such a such a rotation, and these three orthogonal vectors or orthonormal UVW vectors are forming a coordinate frame, it will, the first axis in the top row, so to say, if we will be multiplying that column vector with, post multiplies that column vector with this matrix, we will end up in 1, 0, 0, which corresponds to the x in the canonical coordinate system. Now, the same will happen if we will now post-multiply this row matrix with the vector v. So xv, yv, and cv will be in the aligned in the column. And therefore, the outcome will be 0, 1, 0, which corresponds to the y-axis. And the same holds for the w if we will enter the column vector w, xw, yw, cw, and post-multiply with this matrix, we will end up in 0, 0, 1, so which will correspond to the z-axis. So we can transform this coordinate system, UVW, with such a multiplication into the canonical coordinate system. And we see why these ones and zeros are coming up, because we are essentially performing a scalar product with either parallel or orthogonal vectors. And if we are dealing with parallel vectors, so scalar product with itself, we will end up in 1. And if we are performing a scalar product with vectors which are orthogonal to each other, then the result will be 0. Such a rotation will get us from the xyu coordinates into the canonical coordinates. Now, if we will take this matrix R, and we will create R transpose will look in the following way: xu, yu, zu, xv, yv, zv, and xw, yw, zw. This is our transposed rotational matrix. At the same time, it is the inverse matrix. That one will get us from the, if we will post multiply it with a vector 1, 0, 0, we will get the u coordinate, u vector. So we are rotating with the R matrix, we are rotating the u, v, and w axis into x, y, z canonical coordinates, and with its inverse matrix, obviously the canonical coordinates we can rotate into the u, v, w vectors. This will be very handy for creating a rotation around arbitrary axis. So imagine that we have a rotational axis defined by certain vector A, and we would like to rotate around this axis. So what we can do is, we can do the following. We define that the vector A is the vector W, and we will normalize the W vector, and we will put it into our R matrix. So this is our R matrix, and our W vector is here. So this is our W vector. And now we will need to get the u and v vectors. So this should be v, u and v vectors to create such a coordinate system, and by that system of vectors of this orthogonal matrix which define an rotation. And here we can define the u and v in a meaningful way as we were defining it before. Remember, on the math lecture, through cross products, we can obtain some meaningful v and u vectors. So let's get those, and then we will. These could be fairly arbitrary as long as they are orthogonal to our w vector and to itself, and their length is equal to 1. Now, once we have those, so this is now v and this is now u vectors, and now if we are rotating around this vector, and if we will be rotating around by post multiplication the w vector, we will actually map it to the z-axis, remember? So we will map it to the z-axis. Then the second operation which we will do will be what? What is this? This is a rotation around the z-axis, right? So first we rotated our axis w and the coordinate system UVW, so that the W is aligned with the Z. Then we are rotating around the Z axis with some particular angle phi. And then what is here? This is our transpose R matrix. So we are rotating back. That's how we can realize an arbitrary rotation around an arbitrary axis, if we are given an axis angle rotation as an input, what we should do as a transformation. If we have some rotational matrix and we would be interested what is the axis of rotation, we can compute it in the following way. We take one of the eigenvalues of such a rotational matrix will be equal to 1. And the corresponding eigenvector to the eigenvalue 1 will be the vector of rotation, the axis of rotation. So this is how, from a rotational matrix, we can find out what is the axis of rotation by computing the eigenvector corresponding to the eigenvalue 1. Next interesting aspect which occurs in 3 dimensions is the rotation of normal vectors. So imagine that we are transformation of normal vectors. So normal vectors should be transformed in a correct way, and sometimes they do not transform in a correct way. So if we are transforming certain with, for example, shear, as we can see it here, so we have, this is an original input object, and we transform it. So we shear it, as you can see here, and this shear will, which is an vertical shear, will also shear us the normal. So our shear transformation will be M. This is our shear transformation here, or generally a transformation which is applied M. And we can see that in case of shear, this is what will happen to our vector n. So this is our normal vector at this position. This is our normal vector at the position. This is the tangent vector at this position. And we can see that after applying the shear transformation, the tangent vector remains still tangent to the edge, while the normal vector is no longer perpendicular to the edge. It has been transformed as so that it is parallel to the sides of this parallelogram. So this is not good, and therefore we need to change the normal vectors in a different way. Here is how we can do it. So imagine that we have our normal vector and our tangent vector. So this is our normal vector, this is our tangent vector, and they should always remain perpendicular to each other. A tangent vector is always perpendicular to the normal vector. So this should hold, this expression should hold, and we should see how to realize it. Please keep in mind that here this is the transformed normal vector, and this is the transformed tangent vector. So tangent vector is transforming well, that's no problem. Let's have a look what we can do with this equation, which is the product between the row normal vector with the column tangent vector, which should be equal to 0 as they are perpendicular to each other. Let's sneak in an identity matrix into this expression, which should not change anything. And then we will change the identity matrix into a multiplication of M with its inverse, which results into an identity. And then we just perform an associative operation where we change where the brackets are positioned, and we will realize that MT is equal to transformed tangent. So this is this part, and this part corresponds to, if we should have now a tangent which is transformed perpendicular to the normal, then this is the transformed normal, which is expressed in this way. The n is unknown for now. So, and this means that the nn transposed should be equal to, so this expression should be equal to this expression. And what this leads to, if we write this n t n m inverse should be equal to n nt, n, yeah, which is n t n t, if we take it out from the brackets. And now we can see that n transpose should be m inverse, and n should be m inverse transpose. And this is the result. Here we have it. And we can see how we can obtain such a result. Because you remember we were talking about the adjoint matrix on the linear algebra lecture. So the adjoint matrix was formed from these determinants of the submatrices. And here we have these small determinants of the submatrices. However, they were organized in such a way that it was transposed organization of such an adjoint matrix. So this adjoint matrix is transposed, and this forms our matrix, which we should use for the transformation of normals. Until now, we have been mentioning transformations which are scaling, rotation, reflection, shearing, but perhaps the most natural or simplest transformation we didn't mention so far. And this is translation, simply translating a point at a position to another position. The reason why we didn't mention it so far is that we cannot directly use the transformation matrices. This linear combination of x and y simply cannot express such a simple equation as x equals x plus xt as a translation offset. Therefore, we can see that this form, which we have here, doesn't have this option. The best sort of would be the shearing, but the shearing is somehow including the y into the translation of x, and this would not somehow work without the y component influencing this translation. So what can we do? Well, there is a nice trick which we can apply, and that is, and keep in mind, we are now in 2 dimensions. We will extend our vector or our position coordinates, but one more coordinate, which will be just equal to 1. And also, we will be including to our to our transformation matrix one more row, which will have just the element 0, 0, 1. And we will use this part of the matrix as we were using it before for reflection, scaling, rotation, shearing, as it was before, the 2 by 2 matrix. And this part of the matrix we will be using for the translation. And the translation will be multiplied, as you can see, with this 1. So these translation factors will be multiplied with 1 and not with y, as in case of shearing. So we can see how it will work here. We have the result of our transformed positions and transformed coordinates. So this is the entire formula for x. And here we will have various transformations, including the translation. So while it would, on one hand, be possible to sort of treat the translation separately, as this is not a representation, there is no representation possible for a 2 by 2 matrix to express a translation. This would mean, if we will have a separate handling of the translation, that we will need to do a lot of bookkeeping of when we are concatenating various transformations together, including the translation. Much more practical is that we put the translation into this common matrix vector multiplication framework, but for that we need to extend our matrix by one more row and the vector by one more component. This component is called it's extending this vector with coordinates x and y by the so-called homogeneous coordinates, meaning that we will have this additional value here, which is not the value of the coordinates itself, and it's just serving for the purposes of carrying out the translation. So if we have no other transformation, so we have here, as you can see on the diagonal, just the ones, and we only want to express a translation, we will simply have the x coordinate of the translation in the first row and the y coordinate in the second row, both at the third column. And you can see that simply multiplying will result into the translated vector. Here we can always see that the multiplication will be with 1. So this is the one which we have here. So this will work fine. However, if we will have locations, this is fine. But if we have directions, we do not really want to translate the direction. So how can we ignore the translation for directions, for normal vector, for example? Well, the trick could be we just put here 0, and by that we will multiply the translational factors with 0, and all will be fine. So this is a powerful way how we can add the translation into the other transformations, and together we will be with these homogeneous coordinates be able to do linear transformations and translation, meaning that these all are called affine transformations. We can also think of the geometry meaning of homogeneous coordinates. So for example, if we will have a vector with its coordinates three-dimensional or position with its coordinates x, y, z, and we will have this 3 by 3 matrix, what are we performing with such an operation? This will correspond, in fact, in 3 dimensions to shearing. So we are shearing, but not by the not by the y component, but only the shearing factor is multiplied with the z component. And the shearing factor will be xt for x coordinates and yt for the y coordinate. And we will have the z coordinate unchanged through such an operation. Now we can think of what are these homogeneous coordinates doing. Is that the translation sort of manifests itself through shearing when the z is equal to 1. So on that plane, z equals to 1, we will see the position of our 2D points after this translational trick. So we can see here, once we do not have the z here, but only 1, then our multiplication will be here having this multiplication 1, and all will be, the translation will be successfully carried out. But you can think of it also that this is the result at the plane of shearing at the plane z equals to 1. So as shown on the previous slides, we can have a concatenated matrix where in one part we have our linear transformations, and in another part we have our translation. Now, the question is, if we apply such a matrix, does it mean we are first translating and then rotating, or we are first rotating and then translating? Which one you think is the correct order? Well, this matrix needs to come as a product of these two operations. So we can simply write one order or the other and see whether we will come up with this matrix. It turns out that if we are using the product of translation times rotation, this will yield us the matrix. So it means we have here rotation and translation. Which one will be applied first? First rotation, then translation. So this is RT equals first rotation, second translation. Okay, so this is the translation in the concatenated matrix comes last. Let's have a look at a simple example of using translation in concatenation with other matrices. The point is that sometimes we would like to scale certain object, but we would like to not really or have a clear control over its position. Normally, if you scale an object, its position of its points will be that position will be scaled as a distance from the origin. So if we will apply a scaling of the point XL, YL, this point, based on the scale factor, will be moving closer or more far away from the coordinate origin. As a result, this will mean that if we will be scaling all the points of our rectangle here, in this case, if we are scaling them, they will both be scaling the area of which this rectangle defines, but also the position of the rectangle will be changing based on the scaling factor, either closer to the origin if the scaling factor is smaller than 1, or more far away from the origin if it's bigger than 1. And to sort of have this positioning in control, we will need to first bring our point or to the coordinate origin and perform the scaling there. So what we will do, we will take this point and we will bring it to the coordinate origin. By that, the scaling will not affect position of this point because its new position will be 0, 0. And then the other points, which are the neighboring points, adjacent points to this point, they will have always a 0 in one of the coordinates, so they will be scaling only along the corresponding axis. So only the points across the diagonal will be scaling and moving more far away from the coordinate origin or closer. And by that, we will be scaling the rectangle. However, at this point, we will have only the rectangle after scaling at the coordinate origin, and we might want to move it somewhere else, either to the original location where the XL, was, or to another one. So let's do a simple example where we are performing some controlled scaling and we are changing the location of our scaled object, which is the rectangle. So let's have a first look at our case. We have in the beginning, we have a rectangle defined by the 2 points XL, YL, and XH, YH, and then at the transformed final state, we have the X prime L, Y prime L, X prime H, and Y prime H coordinates of this newly transformed rectangle. So how can we perform this operation? Well, let's have a look at the scaling first. How are we scaling these two? So what we want to do is to basically scale this length to this length. What factor should we use? Well, the factor should be actually the ratio between these two lengths. So how does such a length look like? And I will now draw here the scaling matrix. So the ratio looks like X prime H minus X prime L divided by XH minus XL, right? This is the ratio how we can scale the rectangles so that the X side gets correspondingly larger. And this holds also for the y coordinate. So the y prime h minus y prime l divided by y h minus y L is also the scaling factor which changes this side to be this long. So this is great. We have already the scaling somehow done, but we will be using now also these homogeneous coordinates. Now we want to, however, scale it so that we get the eventual position will be here of this lower left point. So how can we do it? We can do it in such a way that we first move this point to the coordinate origin, as we said, the point xl, yl, um, and that we can do by a translational matrix, which will be identity matrix in the linear transformation part. And we will have here minus xl minus yl, and here 1. This will be the translational matrix, which brings us to the origin. And now, look, we would like to have the final position of this lower left corner or point to be in x prime L, y prime L. So we need to perform the final translation as well. I make it very small here, but here we see that the final translation or the final transformation matrix will be seen as a product of these three matrices. So here I will be putting the translation, which will be again 1 0 0 1 0 0. There is nothing happening with the linear transformation part, and here I will put which vectors? Plus x prime L and plus x y prime L and 1. And this will be my translational matrix, which will bring me from the coordinate origin, this point, to here, and correspondingly also all the other points. We have already mentioned that if we have a several sequence of transformations, we can simply undo them by applying an inverse of this. So here is just a short recapitulation and few examples of what does that mean. So imagine that we have a matrix containing a lot of transformations, M1 to Mn, and we would like to have, and we apply them to a certain uh, set of points, and then we would like to undo it. We simply do the same operations backwards. So either we make an inverse of the final matrix, or we can do the inverses of the individual matrices, but in a reverse order. Certainly, you will appreciate if I want to undo something, and I have done first, let's say, first I translated, then rotated, then scaled. If I do undo, then first I unscale, then I unrotate, and then will untranslate. So the order will be reversed. This is the reversed order of the inverse transformations. Now, instead of computing expensively the inverses of these transformations are sometimes rather simple to define because we know what they are geometrically doing. So the inverse transformation is simple to devise even without calculating the inverse. So for example, if we have this matrix M, which is concatenation of rotation, scaling, and rotation, then if we want to perform an inverse operation, then we know that the rotation matrix is an orthogonal matrix, meaning that it consists of orthonormal vectors, and therefore its inverse is its transpose. So we will just use a transpose of a matrix. For scaling, if we want to scale something, then its unscaling will be to put the reciprocal of the previous scale factors in order to obtain 1, because Sx times 1 divided by Sx, as we see here in the first components of the original matrix and its inverse, will result into 1. So the reciprocal of the previous scale will unscale our object. Then, and the last element here is the uh, first rotation, which we have done, the R2, but again, inverse, which is the transpose in the case of rotational matrices. The last topic of today we will dedicate to coordinate transformations. The notion so far was that we are having some fixed coordinate system, and within this fixed coordinate system, we are transforming the objects, the points, or the vectors in case of some linear transformations. Now, this is just one way how we can interpret of what is happening. The other way of interpretation is that the point which we are transforming doesn't change, but the coordinate system is changing. So there is a interaction between point and the coordinate system, and either the coordinate system is transformed or the point is transformed. And if we transform a point, if we look at it from the transformation of a coordinate system, then it will be the inverse transformation of the coordinate system, which is applied on the coordinate system to get it there where it is. So, for example, we have here a example of a simple translation. So we are translating a point to 1 by this matrix, which has this translation -1, 0. So it will simply move the point to the position 1, 1. So this point will move is one interpretation somewhere here. The other interpretation is that the coordinate system, so this is the direction of the translation. The other interpretation is that the point stays where it is, just that the coordinate system has moved in an opposite direction in order to carry out this relationship between the coordinate system and the point. Why we are mentioning this? Sometimes it is more practical to change the coordinate system, and sometimes it is more practical to change the point. Like, for example, imagine that we have a car simulator and we have our first person viewing, meaning we see the cockpit, and in the cockpit we see all the elements which are basically not moving with respect to the position of the camera because they are static as we are sitting statically in the car. What is moving when the car is in motion is the city or the landscape around. So maybe we do not want to move the car in within the city, but move the city with respect to the car in the opposite direction. So these could be the considerations when we are performing transformations. What should be moved? And often we will be dealing between coordinate transformations from one coordinate frame to another one. Like, for example, the transformation between the canonical coordinate system and some UVW coordinate frame, or it can be named according to the name of the other vectors which are spanning this coordinate system. In this two-dimensional case, which we can see here, we see that we have a UV coordinate system, UV frame, and the canonical coordinate system, which is spanned by the axis x and y and defined by the point O as origin. And the UV coordinate frame is defined by the origin is at the point E. Now, both of these coordinate systems can be expressed by the basis vectors of the other one. Like, for example, also a point can be expressed by the coordinates with each of these coordinate systems. Like, for example, this point P can be expressed as 0, which is the origin of the xy coordinate system, and then some multiplications of the vector x and vector y, forming the linear combination so that the location of the point P is reached. Different values of xp and yp will be used if we will use the coordinate frame u defined by the u and v vectors and the origin point E. So how can we transform between these two can be realized through two operations of rotation and translation, as we can see it here. So if we want to express a point express the point P with in the x and y coordinate system, and we have its UP, VP coordinates at the beginning, the UV coordinate, then we can do it by in the following way. So imagine for where is the point P with respect to UV coordinates? Well, we could say that this would be it would be something like 0.5 U plus or minus approximately 1 V, right? So the V will be having a negative value. So in order to get the point somewhere with respect to the x and y coordinate system to some positive value, we will first need to rotate this point so that we will first align this coordinate system so that it is aligned with our x and y coordinate system. So this will be the rotation which is carried out here, and that will bring the point, so to say, for the x and y coordinate system somewhere sort of here from this image. So this will be the first operation which is done, the rotation, and then we will perform the translation, which will be by the x and y coordinates of the point E. So keep in mind that while here we are using the u and v coordinates of the point, in the matrix we are expressing, so these are the coordinates of our u vector in the xy coordinate system, and these are the coordinates of our v vector in the xy coordinate system. And we are essentially rotating this point uv with this coordinate so that we get the point in the xy coordinate system now below the x-axis, so to say. And then we are performing the translation of by the origin of the xy of the uv coordinate system, the E, and we will end up in the point P with respect to x and y. So we can see that the rotation and translation is an operation which should be done on the transformation of this between these coordinate systems, and this can be expressed also as a concatenated matrix because this is in the right order. So it will be XE, YE, and then XU, YU, XV, YV, and 0, 0, 1. So this is the concatenated matrix of these two as a product of the multiplication of these two. So now we have translated the point with respect to its UV coordinates into the XY coordinates. Let's try to do the opposite. So we get from the XY coordinates of the point into the UV coordinates of the point. How can this be realized? Well, we can already assume or somehow intuitively understand that we will have the original rotation and translation which we were using, and we will just perform the inverse operation of that, which will mean we first perform the translation and then we are performing the rotation inverse of those, which is for the rotation, the transpose. And we can see this matrix exactly being here. So if we want to get the point P into the UV coordinates, so that we will have the coordinates approximately here, U will be 0.5, and as we can see here, it's not -1, but minus 0.7. These are obviously not the coordinates in the XY coordinate system, so we first translate the point P by the vector OE, so we end up somewhere here, and then we are rotating this point further so that it ends up corresponding to this position. So it will be rotated a little bit by this small angle here so that it reaches the position for the XY coordinate system, which is identical to this constellation. So then we will obtain our U and V coordinates of the point P. And the same holds for the three-dimensional case, which we will be often using in computer graphics. So a point in one coordinate system will be expressed through its basis vectors and its origin point, so that we get into the canonical coordinate system, as we can see here on this set of matrices. And if we want to have the opposite transformation, then we will again just inverse this, make an inverse of these transformations, or inverse of these transformation matrices, which are forming the product of the final transformation matrix. So here is the inverse, and we can see we are just the order of the two matrices rotation and translation is exchanged, and we have now here the transposed matrix instead of the original matrix with the UV and W columned vertices. So this is the way how we will be also changing the coordinates for viewing, which we'll be talking on our next lecture. So see you at the viewing lecture soon. Goodbye.